In order to figure out the magnitude of the components of force acting parallel and perpendicular to the diagonal AB of the grade, we can utilize the dot product formulation. So to begin, let's first figure out the parallel component of force of 90 pound along the diagonal line AB of the grade. To do that, we need to take a dot product between the force vector and the unit vector of our diagonal line AB. So to start, let's first calculate the Cartesian vector form of the force. Since the 90-pound force is in 3D space, we first need to resolve it in its component along x, y, and z axis. So we will start the right angle triangle given in green first, and we can project that 90 pound along the xy plane by taking the cos function of 60 degrees. Next, we can take the sine function and it will project the force along the vertical z-axis. Now, once we have resolved our component along the xy plane, we need to further resolve it along the y and x plane using the gray right angle triangle, making an angle of 45 degrees. So to project it along the y direction, we need to multiply our 90 cos 60 with cos of 45, that will project it along the y direction. Whereas if we take the sine function of 45 and multiply that with 90 cos of 60, it will project it along the x direction. Once we have this, we can go ahead and write our force in Cartesian vector form. That will be 90 cos 60 sine 45 negative I, since it is acting in the negative x direction, plus 90 cos 60 cos 45 j and plus 90 sine 60 k, where I, j, and k are the unit vectors of axis x, y, and z respectively. Those are indicating the direction of the components along these axes. Next, let's go ahead and simplify this. It is coming as negative 31.82i plus 31.82j and 77.94k pounds. Now, once we have the force Cartesian vector, next thing is to figure out the unit vector of the diagonal AB. To do that, we know that the unit vector is equals to the ratio between the position vector divided by the magnitude of the position vector. So in order to calculate the position vector of line AB, we first need to identify the point coordinates of these 2 points. So to start, point A lies at a distance of 1.5 feet along the x direction, whereas the y and z component are both 0. Whereas for point B, it lies at the x component of 0, y component of 3 feet, and the z component of 1 feet. Now, once we have these 2 points identified, we can write the position vector utilizing head minus tail. So the components of B minus the components of A will give us the position vector. Here it can be calculated as 0 minus 1.5i plus 3 minus 0j plus 1 minus 0k. Next, we need to calculate the magnitude of this position vector and divide it with the position vector to calculate our unit vector. Once we simplify, it is coming as negative 3 over 7i minus 6 over 7j plus 2 over 7k. Now, once we have both the force vector and the unit vector, we just need to take the dot product between these 2 vectors to figure out the parallel component of force acting along the direction AB. Now remember, for the dot products, we multiply I component with the I component, j component with the j and k with the k component, as I dot I is equals to 1, whereas once we multiply the I component with the j component, the result is equals to 0. So simplifying this give us the parallel component as 63.2 pounds. Now, once we have the parallel component, we can go ahead and look for the perpendicular component utilizing the magnitude relation. That is, square of the magnitude of force equals to the square of the parallel component plus the square of the perpendicular component. Now, rearranging and simplify, the perpendicular component of the force will be equals to the square root of magnitude of force square minus the parallel component of force square. Here the force magnitude is given to us as 90 pound, whereas we have just calculated the parallel component as 63.2 pounds. Simplifying, we get our perpendicular component as 64.1 pounds.